Data conversion. Objectives. In this chapter, we will discuss about data conversion, representation of spatial data, process of conversion, rasterization. In the rasterization, point conversion, line conversion, area conversion. Vectorization, problems in data conversion. Data conversion. Data restricting can be performed by a GIS to convert data into different format. For example, GIS may be used to convert a satellite image map to a vector structure by generating lines around all cells with the same classification, while determining the cell spatial relationships such as agency or inclusions. More advanced data processing can occur with image processing, a technique developed in the late 1960s by NASA and the private sector to produce contrast enhancement, false coloring, rendering, and a variety of other techniques including use of 2D frontier transform, since digital data are collected and stored in various ways. Thus, data source may not be entirely compatible. So, GIS must be able to convert geographical data from one structure to another. Spatial data may be converted between raster and vector data models. In GIS, two types of data model represent spatial data, that is vector model and raster model. In vector models, objects are created by connecting points with straight lines or arcs. An area is defined by a set of lines. In raster model, study area is divided into regular grid of cells in which each cell contains a single value. Representation of spatial data. There are different formats for raster data and vector data are available. Different raster formats like tagged image file format, geotagged image file format, geographic interchange format, joint photographic experts group, digitally elevated model, band interleaved by pixel, band interleaved by line. There are different vector data formats are also available like hardware specific format, digital exchange format, digital line graph, tiger, shapefile, ArcInfo coverage, ArcInfo interchange file. To find existing GIS data for a project is often a matter of knowledge, experience and luck. Since the early 1990s, government agencies at different levels in USA as well as other countries have set up websites for sharing public data. The internet is also a medium for finding existing data from NPO and private companies existing GIS data. Data conversion is defined as the mechanism for converting GIS data from one format to another. It can be easy or difficult. It depends upon the speciality of the data format. Proprietary data formats require special translator for data conversion, whereas neutral or public formats require GIS package that has translators to work with the format conversion of existing data. Process of conversion. Basically, two types of convert process are used for conversion of any existing data. First is a direct translation, second is a neutral format. Types of conversion of existing data. Direct translation. It uses a translator in a GIS package to directly convert geospatial data from one format to another. It is easier to use than other methods. Arc Toolbox in ArcGIS can translate ArcInfo interchangeable files, AutoCAD, DXF, DWG files and MapInfo files into shapefiles or geodatabase. Likewise, GeoMedia can access and integrate data from ArcGIS, AutoCAD, MapInfo, etc. and convert the existing data. Second format, the neutral format. It is public format for data exchange. SDTS format approved by the Federal Information Processing Standards Program in 1992, also known as SDTS or DLG files, is free. Intergraphs and MapInfo provide translators in their software packages For importing the SDTS data, currently there are 5 SDTS profiles available. First, the topographical vector profile covers DLG Tiger, another topology based vector data. Second, raster profile and extensions accommodate digital elevated model, that is another raster data. Third, the transportation network policy comes vector data with network topology. Fourth, the point profile supports the geodetic control points data. And fifth, the computer aided design and drafting profile CAD supports vector based CAD data with or without topology. There are many types of vector formats used in GIS and even more raster formats. It is often necessary to change between the file formats, even if they are both raster or both vector, to make data sets usable together. There are many free and commercial translator and converter software available in the web. Some GIS program supports this type of conversion also. For example, the conversion tool available in ArcGIS can be used to switch between a number of formats. Rasterization. Rasterization is a task of taking an image described in a vector graphic format, that is shapes, and converted into a raster image. Raster image means pixel or dots, for output on a video display or a printer or for storage in a bitmap file format. Types of rasterization. The first type, point feature conversion. Vector to raster conversion involves assigning a cell value for each position occupied by a vector feature. There is no dimension factor assigned for the point feature in a vector data, whereas points in the raster data is represented by a cell value of that point. So, points have at least the dimension of after cell after conversion from vector to raster model. Points are usually assigned to a cell containing a point coordinate. The cell in which the point resides is given with a number or other code identifying the point feature occurring at the cell location. If there are two or more beta points are falling in the same cell, the cell size is large. Schemes like an ambiguous cell identifier assigned or a more complex number in an assessment is implemented. The cell size is chosen in a way that the diagonal cell dimension is smaller than the distance between the two closest point feature. The second type of conversion, line feature conversion. Vector line feature are also converted into raster data model. There are many methods to code the raster cell. One simple method is not giving a value to the cell. If a vector line intersects any part of this method, benefits in a way as it maintains the connected lines in the raster form of the data. The assessment rule often leads to a wider than appropriate line because several adjacent cells may be assigned as a part of the line particularity when the line meanders near the cell edges. This will in turn have more cells are given the value in the conversion. The assessment rule may be applied, for example, assigning a cell as occupied by a line only when the cell center is near a vector line segment. Near may be defined as some subcell distance line passing through the corner of the cell will not be recorded as in the cell. This may lead to a thinner linear feature in the raster data set, but often at the cost of line discontinuous. The third type of rasterization, area feature conversion. Open area features are converted from raster to vector. The method used is similar to that of the line feature. Boundaries of an area are considered as line feature and are converted from vector to raster. The interior regions are then identified and each cell in the interior region is assigned by a given value. During the vector to raster conversion, in an areas, the boundary cells containing the boundary line must be assigned a value. There are several methods to convert the area borderline from vector to raster. One of the common and simple method is a cell is assigned to area if more than one half of the cell is within the vector polygon. That means a cell has the vector polygon feature present in it. If only half of it is assigned to a feature, then the value is given. Another common method assigns are after cell to an area feature if any part of the raster cell is within the area contained within the vector polygon. Assessment results may vary with the method used. The output from vector to raster conversion depends on the input algorithm used. Though if the same input is used, we may get different output layer when a different algorithm is used. The output often depends on a subtle way on the special operation. What appeared to be a quite small difference in an algorithm or key defining parameters may lead to quite different results. Small change in the assessment or rule in a vector to raster conversion operation may result in large differences in output data set, even with the same input. This is often no clear a priori best method. Empirical test or previous experience are often useful guides to determine the best method with a given data. A set of conversion problems, the ease of spatial manipulation in GIS provides a powerful and often easy to use set of tools. The GIS user should bear in mind that the tools may be more efficient at producing errors as well as more efficient at providing correct result. Until sufficient experience is obtained with a suitable algorithm, in this case vector to raster conversion, small controls test should be performed to verify the accuracy of a given method or a set of constraining parameters. Raster format is more convenient to produce color coded polygon maps such as color coded land use map, while map digitizing in vector format is more easier to trace only the boundary. Rasterization is also useful to integrate GIS with remote sensing because remote sensing images are in raster format. The vector to raster conversion requires the following parameters. The field value from the attribute table used to assign values to the output raster. Second, the pixel size for the output raster. Third, the output raster format, that is GeoTIFF, IMG, and fifth, optionally the method of assigning values of point, polyline or polygon to the cell raster, that is maximum length or area or cell center. The most basic rasterization algorithm takes a 3D scene described as polygons and render it onto a 2D surface, usually a computer monitor. Polygons are themselves represented as collection of triangles. The triangles are represented by 3 vertices in a 3D space. At a very basic level, rasterizers simply take a stream of vertices, transform them into corresponding 2-dimensional points on the viewer's monitor and fill the transformed 2-dimensional triangles as appropriate. The quality of rasterization can be improved by anti-aliasing, which creates smooth edges. Subpixel precision is a method which takes into account position on the fine line scale than the pixel grid and can produce different results even if the endpoints of a primitive fall into a same pixel coordinates, producing smoother movement animations. There are many types of vector formats used in GIS and even more raster formats. It is often necessary to change between the file formats even if they are both raster or both vector to make the data set usable together. There are many free and commercial translator and converted software available on the web. Some GIS programs support this type of conversion also. For example, the conversion tool available in ArcGIS can be used to switch between a number of formats. Vectorization. Data may also be converted from the raster to vector data, in which point, line, area feature which are represented in the raster cell format are converted into corresponding vector data coordinate and structured. As a point feature is raster data is represented in the raster cell, that cell is given coordinates of the corresponding cell center. Line feature in the raster data converted into vector lines. This conversion involves identifying the continuously connected set of grid cells that form the line. The location of the vertices along the line are taken as the cell center line may be smoothened using a mathematical algorithm to remove the stair-step effect. When vector data is not readily available for setting up a GIS database, the vector data is normally created from existing paper maps or natural source images such as aerial photos or satellite imagery. Because of its abstract form, vector data has traditionally been acquired using manually tracing with a digitizing tablet from paper maps or base maps. The disadvantages of the manual method are slowness and lack of accuracy, because the human hand is capable of resolution only to the level of 40 dots per inch DPI. For a typical contour map, it can take one skilled operator 1 or more weeks to trace all the lines manually. The intense labor requirement makes large mapping and GIS project difficult and expensive to implement. With the development of scanning technology, map scanners have become cost effective and capable of high resolution in the range of 100 to 1200 DPI. Moreover, similar development in automated raster to vector conversion have made it possible to take a paper map, scan it, accurately convert it into a vector format. This method uses computer to automatically extract vector data from the scanned image and eliminates the manual tracing process. Using raster to vector conversion technology, large scale map digitizing or GIS database creation project can now be accomplished in much shorter time with less demand on human sources. While vector data structures provide a simpler and more abstract data representation than raster images, an automated conversion from raster to vector or so-called vectorization process is not an easy task. Although the opposite direction, that is from the vector to raster, is quite trivial and straightforward. There have been extensive research efforts focused on the issue involved in raster to vector conversion during the past decades. Process of conversion. A complete raster to vector conversion process includes image acquisition, pre-processing, line tracing, text extraction, shape recognition, topology creation and attribute assignment. The image acquisition process generates the initial raster image at the certain spatial resolution. The quality and the resolution of the raster image are key factors for the quality and accuracy of the vectorized data. It always recommended to start with clean and sharp originals and scan at reasonable resolution. Line tracing process. The line tracing process extracts two types of lines, that is center line and the boundary line. The center line method tracks the center pixel within a raster line and follow the line until it reaches an intersection or the end of the line. The boundary line method tracks the boundary pixel of a color region to get closed polygons. Although there have been many methods developed for a line tracing, they can be divided into two groups: line thinning and line following. The line thinning method is more of a global approach which iterates through entire image in multiple passes and eliminates boundary pixel during each iteration until only one skeleton pixel are left. The line following method uses computer intelligence to analyze line shapes, thickness and intersection to follow the line centers. This method is frequently employed in semi-automated interactive tracing, while line thinning based methods are used for fully automated conversion of complex images. After lines are extracted, they are labeled with line attributes or elevation if contours. Closed polygons can be generated from line segments if needed. Control points are defined and applied to geo-referenced the vector data to a target projection system. Problems in data conversion. Several issues involved with the actual conversion of vector data to raster format have been identified. POVAR noted 3. First, polygon filling the interior regions of a newly rasterized polygon with the correct classification value. Second, cut cells, choosing one classification for a cell that actually contains more than one class. And third, cell size. Choosing a cell size that balances the size of the raster file with the quality of the conversion. Several issues involved with the actual conversion of raster data to vector format have also been identified in this. Pre-processing raster file to produce raster to sheer volume of information that is to be processed. Second, enhancement of the raster image. Third, post-processing of data once it has reached the vector format. And addressing differences in appearance of polygons represented in raster and vector format. The raster to vector translation may present yet another problem. Each vector created from a raster file contains the vertices of each and every corner of each and every grid cell that it bounds. Each line is composed of a series of x and y coordinate, that is vertices, that when combined form a series of short segments, where when these short segments are combined they form a line, where the newly formed line passes between several grid cells in a straight line. Extraneous vertices are created at the corners of each and every grid cell. Summary: any vector data containing point, polyline, polygon can be converted into raster dataset and vice versa. The vector data can be stored in shape files, databases or various other GIS file formats. The raster data are made of pixels or grid cells and can be represented by a discrete categorical data, that is example land cover maps, or non-discrete continuous data, for example satellite images, surface data. The process of conversion of vector to raster data is called rasterization, and the vector to raster conversion requires the following parameters: the field value from the attribute table used to assign to the output raster, the pixel size for the output raster, the output raster format, that is GeoTIFF, IMG, and optionally the method of assigning values of a point, polyline or polygon to the cell raster, that is maximum length or area cell center. The output of the rasterized vector looks like a gridded version of the vector. It depends on the grid cell size. The process of vectorization refers to the conversion of raster to vector dataset. The raster dataset can be converted to vector point, polyline or polygon. In order to convert raster to vector, the following parameters should be provided: attribute field of the input raster, dataset which will become an attribute in the output vector class, determining if the output polygon or polyline will be smoothened into simpler shapes or conform to input raster cell edges, that is the stair stepping. For each raster pixel or gridded cell, a point will be created at the center of the cell. The non-discrete continuous raster data have to converted to the categorical data type before converting to vector data. The conversion of vector to raster and raster to vector degrade the data to some extent, causing loss of details, accuracy and changing the original data. Moving from vector to raster is not that difficult. A line or polygon is simple given a pixel value. This is a time consuming and complicated procedure. Sometimes it is impossible to exchange and one cannot move between the format. If this is the case, the math has to be redigitized. In other instances, they are just approved translation and a data is lost in exchange, raster to vector or vector to raster conversions.